Now we study the jointly Gaussian random variables and some of the properties of the Gaussian random variable. So we already studied the Gaussian random variable. If we let x is a Gaussian random variable, its probability density function fx of x is equivalent to 1 upon 2 pi sigma x whole square e power minus 1 by 2 times x minus mx whole square. So this is the probability density function of the random variable x, and the corresponding random variable is called as the Gaussian random variable. Now we consider two random variables that are jointly Gaussian. So here x and y are said to be jointly Gaussian if the joint probability density function fxy of x comma y of these two random variables. See, this is the probability density function of this random variable. So that's why we call this particular random variable as the Gaussian random variable. If the probability density function of a random variable is in this form, then the corresponding random variable is said to be Gaussian. Now we are letting x and y are jointly Gaussian, then the probability density function, that is the joint PDF of these two jointly Gaussian random variables, will be equivalent to 1 divided by 2 pi into sigma x sigma y under root 1 minus rho square. Rho is the correlation coefficient that we already know. This is e power minus 1 by 2 times 1 minus rho square multiplied with x minus mx by sigma x whole square plus y minus my divided by sigma y whole square minus 2 rho into x minus mx multiplied with y minus my divided by sigma x sigma y. So you close this. See, this constant or this factor is multiplied with this, and this, and then so this entire term is in the exponential, and this is common factor to this, and this. So this is a big equation. The probability density function, that is the joint PDF of the two random variables x and y, is this. Then x and y are said to be jointly Gaussian random variables, where the sigma x square and sigma y square are the variances of the two random variables. Mx is the mean value, rho is the correlation coefficient of the two random variables x and y. See, in the case of single random variable, there is no rho term because there is only one random variable. But in this case, we are finding the correlation coefficient. There is a correlation, which is a measure of correlation between the two random variables. So that's why we included that term also. So that's why the equation has the sigma x, sigma y, rho, mx, my values. All these are constants. Mx mean value of x, my mean value of y, sigma x, sigma y, these are the constants, and rho is also a constant. Now we let rho is equivalent to 0. That is, the correlation coefficient is 0. Then this fxy of x comma y is equivalent to 1 divided by 2 pi sigma x sigma y. This is e power. See, when rho is 0, this becomes 0. It is minus 1 by 2 into x minus mx divided by sigma x whole square plus y minus my sigma y whole square. Now, can I write this as 1 divided by under root 2 pi sigma x whole square, so e power minus 1 by 2 into x minus mx divided by sigma x whole square multiplied with 1 divided by under root 2 pi sigma y whole square. This is e power minus 1 by 2 y minus my sigma y whole square. See, we have 2 pi under root 2 pi into under root 2 pi. That is under root 2 pi whole square, that is 2 pi sigma x square. Under root sigma x square is sigma x and this is sigma y. Same equation. Now, if you consider the first term, this is fx of x multiplied with f y of y. See, what is fx of x? It is the marginal density of x. Fy of y is the marginal density of y. See, what is the relation that we obtained? Fxy of x comma y is equivalent to fx of x multiplied with fy of y. If this condition is satisfied, the two random variables are said to be independent. See, when rho equivalent to 0, the Gaussian random variables. When rho equivalent to 0, the jointly Gaussian random variables are independent to each other. So these are jointly Gaussian and independent to each other when rho equivalent to 0. Rho equivalent to 0 does not imply the independence. When rho equivalent to 0, the random variables may be independent or dependent. But in the case of jointly Gaussian random variables, when rho equivalent to 0, we can say that the random variables are independent to each other. So this is applicable to this case only. If you consider any two random variables, when rho equivalent to 0, that doesn't mean that they are independent. See, when the two random variables are independent, rho equivalent to 0. But rho equivalent to 0 doesn't imply the two random variables are independent. That is, one statement is right, the reverse is not true always. But in case of jointly Gaussian random variables, when rho equivalent to 0, the two random variables are independent of each other, or otherwise here the two random variables are independent, that's why rho equivalent to 0. So here in this case, both the statements are valid. The second statement may not be valid in all cases. We consider a case, the joint PDF is constant. So when this particular joint PDF will be constant, when it will be constant? See, 2 pi is a constant, sigma x, sigma y are constants. This term is also constant. So this entire term is a constant and this term is also constant. See, if this term is constant, then fxy of xy is also constant. Is it? Now we consider this particular term, that is x minus mx divided by sigma x whole square plus this minus this is equivalent to constant. If that is a constant, automatically this exponent is a constant and this is a constant. So fxy of x comma y is also a constant. We let that is a constant and we try to plot the contours of the jointly Gaussian random variables in the xy plane and see how these two random variables are related to each other or different values of rho. Is x minus mx divided by sigma x whole square minus 2 rho x minus mx into y minus my divided by sigma x sigma y plus y minus my divided by sigma y whole square. Let this is equivalent to c square. I am letting it is a constant, where c is a constant. So if this term is constant, definitely this fxy of x comma y, the joint PDF is also constant. So with this assumption, we try to see how the two random variables are depending on each other for different values of rho, different values of sigma x, sigma y, different values of mx and my. So as a first case, I let this rho is equivalent to 0. When rho is 0, this x minus mx divided by sigma x whole square plus this is y minus my sigma y is equivalent to c square. Is it right? So obviously this equation indicates what? Circle. How it will be circle? See, this is the equation of an ellipse centered at mx and my. Okay. So this is an equation of an ellipse centered at mx my with the radius, that is the maximum and minimum radiuses depending on the sigma x and sigma y values. Is it right? So here in case A, we let mx equivalent to my equivalent to 0 and sigma x equivalent to sigma y, which is equivalent to some sigma. So therefore, what is the equation? This is x square plus y square is equivalent to c sigma square. Is it right? This is 0, this is 0, this is equivalent to this, and that we are letting sigma. So therefore, x square plus y square is equivalent to c sigma square. So what this equation indicates? It's the equation of a circle centered at the origin. So here we let the xy plane and we try to plot the relationship between the two random variables. How the two random variables are related to each other. When rho is 0 and these conditions are satisfied. Let this is y and this is x, this is the xy plane, this is origin. So this radius equivalent to c sigma square. C sigma, because it is in the form of x square plus y square is equivalent to r. So r is the radius. So this is the contour that represents the relationship between the two random variables x and y. Here x and y are jointly Gaussian random variables. Here the assumption is the joint PDF is constant. X, Y are jointly Gaussian and we are letting the joint PDF is constant. That is this term is equivalent to constant, and first we assume rho is 0 and mx, my are also 0, sigma x equivalent to sigma y. Then this equation represents a circle, and in the xy plane we can represent the relationship between the random variable y and x by this. Alright. See here, when the two random variables are jointly distributed, if you have the idea about, or if you have the knowledge of one random variable, you can get the information about the other random. For example, if you know about the random variable x, this is a constant, so definitely we can get some information regarding the random variable y, or otherwise we can estimate one random variable given the other random variable. So that's why we are studying the joint distributional density functions, and we are performing some operations on the joint probability density to obtain the various joint moments like correlation, covariance. These are very, very important. So from that we obtain the correlation coefficient rho, which is equal to covariance of xy divided by sigma x into sigma y. That is a measure of correlation between the two random variables. When rxy equivalent to 0, the two random variables are said to be orthogonal. When rxy equivalent to 0, the two random variables are said to be orthogonal to each other. When covariance of xy equivalent to 0, then the two random variables are uncorrelated. If sigma xy equivalent to 0, two random variables are uncorrelated. That is, they are not correlated. When sigma xy equivalent to 0, what is rho? Rho is 0. So when rho is 0, the two random variables are uncorrelated. So that's why when rho is 0, we are saying that the two random variables are independent to each other because they are not correlated. So that condition is true when the two random variables are jointly Gaussian. Okay, now we let mx equivalent to my equivalent to 0 and sigma x is greater than sigma y. Then what is the equation? X divided by sigma x whole square plus y upon sigma y whole square is equivalent to c square. So this is an equation of ellipse. This is x, y. So these are called the contours of the jointly Gaussian random variable, or contours of the joint density function. So again it is centered at 0. Why? Because we are letting mx, my equivalent to 0. See, if mx, my not equivalent to 0, then it will be centered at mx, my. See, here when y equivalent to 0, what is x? X equivalent to c sigma x. Is it? This is c sigma x. When x equivalent to 0, y is c sigma y. So here we are letting sigma x is greater than sigma y. So definitely this radius is more. This value will be minus c sigma x. This will be minus c sigma y. So it is an ellipse. Now we let see here also what is rho. Here also rho is 0. Now let mx equivalent to my equivalent to 0 and sigma x less than sigma y. So there is no change in the equation, same equation. is c square. Now it will be like this. Is it right? This is 0, c sigma x, c sigma, because sigma x is less than sigma y. Now, in case 2, case B, we let rho is not equivalent to 0. So here when rho is not equivalent to 0, we consider rho is equivalent to plus or minus 1. Rho tends to plus or minus 1. Magnitude of rho is less than or equivalent to 1, or otherwise rho is lying in between minus 1 and plus 1. And also let sigma x, sigma y equivalent to 1. So in this case, what is the equation? X minus mx whole square minus 2 rho x minus mx into y minus m. Here, if you let this mx equivalent to my equivalent to 0. So here, when this rho tends to plus 1, that equation can be represented as this angle is equivalent to 45 degrees. When rho tends to plus 1, the equation will be like this, or the relationship between y and x will be an ellipse again. But it is making an angle with respect to the x-axis, that is equivalent to 45 degrees. When rho tends to minus 1, it will make an angle of 135 degrees. This angle is equivalent to so that is the difference. So when rho equivalent to 0, we obtain the ellipse, but here also it is an ellipse. But what is the difference between the previous and this? See, in the previous case, when rho equivalent to 0, the two random variables are independent. Follow. In this case, when rho is tending to plus or minus 1, the two random variables are linearly dependent. Here, the two random variables are linearly dependent. That is the difference between the case 1, case A and case B. In case A, we assume rho is 0. Here we assume rho is tending to, or rho is not equivalent to 0. This is the case when rho not equivalent to 0. See, in case of jointly Gaussian random variables, rho equivalent to 0 indicates the two random variables are independent. Rho not equivalent to 0 indicates they are linearly dependent. So these two are linearly dependent on each other. Why it is linearly dependent? Why the term linearly dependent? See, for example, if you let rho equivalent to 1, so when rho equivalent to 1, what you are getting? X square minus 2xy plus y square equivalent to c square. Okay. So this is x minus y whole square is equivalent to c square. This implies x minus y is equivalent to c, x minus y is equivalent to minus c. Therefore, x and y are linearly related because c is a constant. Similarly, when rho is equivalent to minus 1, it is x square plus 2xy plus y square is equivalent to c square. It is x plus y is equivalent to c, x minus y equivalent to c. Okay. Minus. So again, both are linearly dependent. Therefore, when rho is not equivalent to 0, the two random variables are linearly dependent. Linearly dependent. When rho equivalent to 0, they are independent. So all these are the properties of the jointly Gaussian random variables for different values of rho. See, in the last case, we also assume the variance of the two random variables is equivalent to 1. Is it? See this equation. Where is the sigma x here? Sigma y, sigma xy. We assume sigma x equivalent to sigma y equivalent to 1. Here, see. Sigma x equivalent to sigma y equivalent to 1. And rho is not equivalent to 0. Therefore, the two random variables x and y are linearly dependent.